irreducible SU2 representations of the fundamental groups of link complements. So representations of the fundamental groups of three manifolds has always been one of the major topics in low-dimensional topology. For example, there is a conjecture that's been out there for a couple of decades now, which states that if M is a closed three-manifold and say closed and integer homology S3, so saying that it's an integer homology S3, that's the same thing as saying that it has exactly the same homology groups as S3 in integer coefficients. Then its fundamental group it's an irreducible SU2 representation. Historically, using representations or linear representations of the fundamental groups of three manifolds was one of the most fundamental way of investigating the properties of three manifold groups. So these kind of questions have attracted a lot of interest. And there's another version of this conjecture in knot theory, and in fact this was a conjecture that was included in the older version of Kirby's list, and it was attributed to Cooper, which states that if K is a knot, then pi 1 of the complement of K admits an irreducible representation in SL2C. The group SL2C is of particular interest is because representations into SL2C is related to hyperbolic structures on the corresponding three manifolds.
And sky modules.
And yes, and nowadays we also have the language sky modules, and we know that these are all very closely related. So it turns out that Cooper's conjecture was solved by Kronheimer and Moravka using their work in instrument for homology. So in fact, Kronheimer, Moravka established that in the, I think it was in the early 2000s, that if, I should have said that K has to be non-trivial because otherwise pi 1 of the complement is abelian group and every representation has to be reducible. So if K is a non-trivial knot, then pi 1 of the complement of K, it not only admits an irreducible representation SL2C, but actually admits an irreducible representation in SU2. And moreover, we actually can find such a representation such that the image of the meridian has traced 0. So this is a particular technical addition that we can make into this claim. So such that the image of the meridian of K has traced 0. But let me just remark on this additional statement that we just make. So SU2, of course, it's given by the set of matrices, let's say A, B, C, D, and let's call this matrix M, in complex coefficients such that the determinant of M equals 1 and the transpose conjugate of M is
So special unit.
I
mean, this is special and second.
Special unitary, yes. Special unit, second 2 by 2 special unitary 2 by 2 matrices. And in particular, if you look at this thing as a Lie group, then SU2 is diffeomorphic to S3, and we can kind of see that directly by writing down the coordinates. So if you just write down A, B, C, D using real coordinates, so that we have 8 variables, and write down these 2 conditions, and after some simplification, it exactly gives us the equation of the unit ball in R4. So we know that SU2 is diffeomorphic to S3. Actually, another way of understanding the structure of SU2 is to think of that as the group of unit quaternions. So, on the other hand, that the quaternions is 4-dimensional real, 4-dimensional algebra spanned by one ijk, and let me just recall that ij equals k, jk equals I, ki equals j, and then it's anti-commutative on these generators. So these are the definitions of the algebraic structure on quaternions. Then we can consider the unit sphere S3 in H and be the unit sphere. So that is saying that S3 is given by A plus BI plus CJ plus DK, such that A squared plus B squared plus C squared plus D squared equals 1, and in this case A, B, C, D are all real coefficients. Then it's not too hard to verify that this S3 actually forms a group, in the sense that if we take 2 elements on the unit sphere, then their product is also on the unit sphere, and if we have an element on the unit sphere, it has a unique inverse that's also on the unit sphere. So this S3 actually forms a group, and it's like by some straightforward computations using matrices, we can verify that this S3 is exactly isomorphic to this SU2. And again, these all follow from pretty straightforward computations. The correspondence pretty much just comes from writing down explicit correspondences in coordinates of matrices. So how does that have to do with?
So maybe first you can comment from the beginning. Why you assume irreducible? Is it true that if there's non-trivial irreducible, then this piece which is irreducible?
Yes. So of course, a representation SU2 can be reducible or irreducible. So here we're thinking of SU2 representations as 2-dimensional complex representations. So in that case, if we have a representation that's reducible, then that reduces to the direct sum of 2 U1 representations. In other words, that becomes a direct sum of 2 abelian representations. So reducible SU2 representations are actually relatively easier to understand because every homomorphism into U1 passes through the abelianization of the group, because U1 is an abelian group, and the abelianization of pi1 is H1. So understanding the reducible representations of SU2, it just corresponds to understanding the H1 of the manifold. So, and in particular in this conjecture, if we just assume that S3 is an integer homologous sphere, then there's no non-trivial reducible representation. So this conjecture is the same as saying that then pi1 admits SU2, non-trivial SU2 representation. So I think it's a similar case here. So in this case, if we look at the knot complement, then H1 is just Z, and then we understand very well what the abelian representations are, and this theorem states that there are other representations. Yeah. Thank you very much for the question. So, okay, so now let me comment on this condition that the image of meridians have trace 0. So if SU2 is a 2x2 matrix, then we can look at this, well, it's the set of a collection of 2x2 matrices. Then we can consider the subset of that where the trace of the corresponding element is 0. So it turns out that the following conditions are equivalent. So if we have M in SU2, let me actually write it on a separate board. So M in SU2 has trace 0 if and only if its square is -1. And this holds if and only if M is given by AI plus BJ plus CK in H with A squared plus B squared plus C squared. So In other words, a traceless element in SU2 are the elements that have order exactly 4 as an element in the group. Or we can view that if we look at this correspondence with the unit sphere in H, so then the locus of all those matrices form a 2-dimensional sphere. And it's a 2-dimensional sphere that are in the 3-dimensional space spanned by IJK. In a certain sense, this is kind of the purely imaginary elements in the quaternions. If we think of this A term, so this coefficient in front of 1 as the real part, and the IJK as some kind of purely imaginary part, then this condition is saying that the real part has to be 0, and we only have a purely imaginary part of the matrix. So it turns out that this we can have a stronger version that verifies the Cooper's conjecture, which states that not only we know we have an irreducible representation, but we can also control the trace. We can also say something about the meridian, the image of the meridian.
It was all induced about a polynomial, yeah, which have trace 0.
Yes. So all these kind of discussions are also related to a polynomials, although I haven't really thought much about that. It's related to a polynomials, and it's also related to other, for example, the Casimir invariant of 3 manifolds and other aspects of 3 manifold invariants. So that's why irreducible representation as you do is kind of attracted a lot of interest in the past. Oh, and by the way, so this set is actually just one conjugation class. So let me write this as so the properties. 2, 1, 2. If we have 2 elements, so let me write this M1 and 2 in C2, both have trace 0, and M1 and 2 are conjugate. In fact, more generally, the trace gives a complete classification of the conjugation classes in SU2. And again, that follows from like pretty straightforward matrix theory. So it follows from straightforward computations using matrices. So another way of making this statement is saying that we can not only know that we have a irreducible representation, but we can also fix the conjugation class of the meridian. All right, so the theorem that I would like to present today is a generalization of Kroheimer and Brodka's result to the case of links. In the case of links, so let me question. Without in the case of links, actually, we do have examples. We do have examples of non-trivial links whose fundamental group of the fundamental group of the complement do not admit any non-abelian or irreducible SU2 representations. One of the most straightforward examples is actually the Hopf link, because if we look at the pi 1 of the complement of a Hopf link, this is actually an abelian group. So, of course, it cannot admit any irreducible representations in SU2 because it has to, any homomorphism of this group to SU2 has to factorize to an abelian group. And by standard representation theory, we know that every representation has to be reducible. So we also have some more, well, it turns out that if we require that the meridians are all traceless, then there are also some other examples. So for example, we have something like this. And in this case, the fundamental group of this, let me just write down presentation of the fundamental group. So this follows from the algorithm of working representation, which is something that allows us to write down a presentation for the fundamental group of link complements from any diagram. And in this particular case, after some simplifications, we see that this is given by the group with 3 generators x, y, z, such that x and y is commutative YZ are commutative. It's kind of a direct generalization of what we saw from the Hopf case. So whenever the two components form a Hopf link, that actually forces the corresponding generators to be commutative, and it turns out that these are all the relations. So in this case, well, it turns out that for this case, we can find irreducible SU2 representations of this group. It's actually not that hard to construct those. For example, we can take the image of Y to be 1 and X and Z to be some non-commutative pairs. So in this case, let me write down rho from pi 1, 3 to x2. That takes x to, let's say, I, y to 1, and z to j. And of course, in this case, I and 1 are commutative, 1, j are commutative. So this is a valid representation of this particular group. Its image is non-abelian, therefore it has to be irreducible. So we know that in this case, the fundamental group does have irreducible SU2 representations. But if we further require that all the meridians are mapped to traceless class, then actually we cannot construct anything non-abelian because on the other hand, let me just write that. If we require that rho x, rho y, rho z are all traceless, z will have zero trace, then rho must be abelian. And this is because, so let me write proof of the claim. So since rho x has trace 0, then we know that after global conjugation, we can just assume that rho x is equal to I, let's say, because all traceless elements are conjugate to each other. So we may assume rho x equals I, and in this case, and again that follows from kind of straightforward matrix computation, but the only traceless element in SU2 that is commutative to I is our plus minus I. So the only trace 0 element in SU2 that is commutative to I are I and minus I. So that means if we require that rho y has traceless, and this condition tells us that the images have to be commutative to each other, so that actually implies that rho y has to be I or negative I. But of course, we apply the same argument to the commutator of y and z, so that also implies that rho z is I or minus I. And in conclusion, we see that everything is mapped to I or minus I, and therefore the image of the whole group is abelian. And therefore, if we require the meridian traceless condition, then actually we do have more complicated examples where the image has to be abelian. Well, actually, you can imagine that we can have more complicated examples like that. So, for example, we can have a connected sums of Hopf links. So, for example, if we have we can consider something like that. And it turns out that the computation is very similar. This is a very picture was very nicely, but so this can be regarded as a connected sum of 4 Hopf links. And it turns out that in this case, pi 1 S3 minus L is given by, so let's just give everything a name. So this is x1, x2, x3, x4, x5. Then it's fundamental group. Again, this follows from straightforward computations. It's a group with 5 generators such that every pair of linked components creates a commutativity condition. So exactly the same argument will tell us that every representation of this map, of this group, into SU2, such if we require that all the generators are mapped to traceless class, then the image has to be abelian. So our main theorem claims that these are all the possible counterclaims. So this is the theorem I would like to present, and it was joined with Yixian from 2021, probably 2022. And we state that if L is not given by connected sums of half links, then I1 S3 minus L admits an irreducible representation in SU2 such that images of meridians have zero trace. And actually, once we have this theorem, that immediately implies a corresponding result about the existence of representations in SU2 without this meridian condition. Because every link that's given by connected sum of half link has to be given by something like this. So in other words, there's basically just a tree underlying this picture. And then for every vertex of the tree, it corresponds to an on knot, and every edge of the tree corresponding to a half link in between those two on knots. So those are all the knot links that can be given by connected sums of half links. And for those links, we can directly check which ones of them actually admit irreducible representations in SU2 without this meridian traceless condition. And if we just run this computation, the conclusion is that, let me write it as a corollary. Assume L is not the on knot or the half link. Then I1 minus L is irreducible representation. So that also completely classified the links whose fundamental group admits irreducible SU2 representations. And let me just remark that, so actually our proof, so if we make one further corollary from this statement, then that implies that if L is the on knot or the half link, then the fundamental group has to be non-abelian in the first place. So we actually, but this is actually a classical result that was known in classical knot theory. But let me just write as a corollary. So if L is not the on knot or half link, then I1 is a complement is non-abelian. But our proof actually doesn't use this fact, so this kind of gives an alternative proof for this classical fact about characterization of abelian fundamental groups and non-complements.
So you should explain me, so why your theorem does not follow this famous Jones conjecture that only trivial knot has trivial Jones polynomial?
Oh, yes.
It doesn't follow, yeah? No.
So it doesn't quite follow because it's not quite, that's exactly why the Jones polynomial is more mysterious than this kind of constructions, is because for the Jones polynomial, really, so far, at least from the mathematical side, the only way to understand the Jones polynomial is through some kind of two-dimensional field theory, or either by looking at sky algebras
Yeah,
or
because
brackets.
you're using formation, putting A equal -1 or something like this, which is SL2 representation, yes?
Right, exactly right.
So
If you plug in special numbers,
solve.
that corresponds to some representations, but I don't think that's strong enough to actually give us a detection result for the trivial knot. So one of the reasons that all of these are possible is because we actually have, nowadays we have a very deep tool package that we can use to understand SU2 character varieties of three manifolds using Floer theory. And that's what I'm going to talk about. So it turns out that all these results are proved through Floer theory that allows us to use analytical methods and homological methods to understand the properties of technical varieties or representation varieties of fundamental groups of three manifolds. So now let me talk about a little bit about the ingredients in the proof. And as I mentioned before, the main ingredient in the proof is Floer theory. And by Floer theory, we should really understand it as some kind of an infinite dimensional version of Morse theory. So I guess, can I just, are we all familiar with the definition of a Morse function? Oh, all right. So I'll talk about it. Don't worry. I'll talk about it. So Morse function is actually a finite dimensional function that's kind of generic in the sense that every critical point has a non-degenerate hashing. So, well, that's actually the definition. So if M is a smooth manifold, a function f from M to R is Morse if at every critical point of F, so let me give it a name, every critical point P of F, so this is saying that differential of F is 0. P, we have that the hashing of P and F, and we can just, so for the hashing, this is exactly just a collection of all two second-order derivatives, and we form a symmetric matrix out of that under local coordinates. And this is non-degenerate. And by the non-degenerate, I mean that the determinant hashing P of F is non-zero on the local coordinates. One of the most fundamental properties of Morse functions is that once we know a function is Morse, then near every critical point, this function always has a standard form. So, well, for those of you who have taken, for example, courses in dynamical systems, you might know that near a critical point of a function, or even if a smooth function, a lot of complicated things can happen towards the behaviors of the function. For example, well, the critical point may not even be an isolated point, or there may be a very complicated flow lines of the gradient trajectories that creates difficult questions about dynamical systems. But if F is Morse, actually everything is pretty simple near the critical points, because we have this theorem. So if F is Morse and P is a critical point, then after there exists a coordinate chart near P such that F is given by sigma, let's say I from 1 to M xi squared, and then minus sigma I from M plus 1 to N. So in other words, if we have a Morse function, then each critical point so basically is given by just a quadratic function. And it's the simplest possible quadratic function we can ever write down that has a non-degenerate hashing.
In extreme, it's maximum and minimum.
Well, if depending on how many positive signs we have and how many negative signs we have. So it turns out, so after having this form, we see that the only thing that's undecided is the number of positive terms and the number of negative terms. So if they're all positive terms, then we have a local minimum. If they're all negative terms, in other words, if n equals 0, we have a local maximum. If we have a certain number of positive and a certain number of negatives, then this is kind of the so-called saddle point of a non-degenerate function. And in that case, the number of positive terms corresponds to the number of positive eigenvalues of this Hessian. So this is a real symmetric non-degenerate matrix, so it can be diagonalized. And the number of negative terms corresponds to the number of negative eigenvalues of Hessian. So this is kind of a nonlinear version of the classification of quadratic forms. So if you still remember from linear algebra, like if you have a Hessian, which is a symmetric to Riemann matrix in real coefficients, so we can view that as a quadratic form, then every quadratic form in R coefficients can be diagonalized by an orthogonal matrix. And this is kind of a nonlinear version of that, which tells us that, in fact, if the second derivative of f at a critical point gives us such a non-degenerate symmetric matrix, then not only we can diagonalize all the second derivatives by orthogonal transformation, we can actually diagonalize the whole function. So the function itself becomes a diagonalized standard quadratic function. And actually, basically, the proof also works the same way. So we just go back to the proof of the diagonalization and figure out a nonlinear version of it. So that's very nice. That tells us that for Morse functions is a very nice class of functions. And another theorem actually tells us that Morse functions always exist on every manifold. And it's not always exists, but actually it's dense, and it forms a subset of bare second category in whatever topology that we choose on functional spaces. So for example, if we consider all the C2 functions on M, to talk about Hessian, we need at least C2. So assuming we take the class of all the C2 functions on M, then that forms some kind of metric space with respect to the C2 norm. It's actually a complete metric space by standard analysis. And then the subset of Morse functions forms a subset of bare second category in the sense that its complement is a countable union of subsets with whose closures don't have interior.
Particular dense.
And in particular, this is dense with respect to the C2 metric. And the same thing also applies to CN metrics and smooth metrics. Another way to say that is that if you just give me a random function that may or may not be Morse, then we can always shake that function a little bit, arbitrarily small shake, such that that function becomes Morse. So Morse is actually what we call a generic phenomenon. It's like for anything that we're given, we just shake that a little bit and it will become Morse. So that gives us a very nice way of understanding the topology of manifolds from functions. So we can always choose a Morse function and try to understand the manifold, topology of the manifold from the Morse function. And that kind of idea can also be formulated as some kind of localization idea in topology. That is, instead of looking at the topology of the whole manifold, we can reduce that problem to looking at some finite subset or behaviors of the manifold near some finite subset. So the general philosophy of this line of ideas is sometimes called the localization. And from that point of view, we can say that Morse function allows a localization in this theorem that, or let me just write it as a general philosophy. Behavior of f near critical points can allow us to study the topology of the manifold. As an example to this philosophy, let me write down another theorem which states that, so if, in this case, let's assume that M is closed, then and f is Morse with critical points, let's say P1 all the way to Pk. And for each Pi, we can look at its diagonalization, the diagonalization of f near the critical point, and we count how many negative terms are there in this. And that is called the negative index of that critical point. So for each Pi, so let's say let n of Pi be the number of negative terms in the, so let's just call that the standard form of f. Near Pi. then a very beautiful result that we have is that if you look at the alternating sums of those, so sigma of -1 to the n of pi, I from 1 to k. So this is kind of a sign counting of the number of critical points, where if the critical point has an even index, then it's counted as positive. If the critical point has an odd number of negative terms, it counts as negative. This alternating sum is exactly equal to the Euler number of that. And in
This
fact,
Annie can teach us, because probably you teach her Handel decomposition, and of course we see Handel's correspondence.
yes, this comes from Handel decomposition subcritical points. But so historically, this was first discovered by Handel decomposition. So this is because once we have a Morse function, there's associated Handel decomposition, or alternatively, there's associated CW complex decomposition of the manifold, and then this NPI, this number exactly corresponds to the index or the dimension of the handles or cells, and therefore we have this formula. But then later, Edward Witten proposed that we can have a different way of looking at this by saying that, in fact, the homology groups of M can be recovered from the Morse function as follows. So, the idea of Witten is that we can actually build a chain complex out of a Morse function. So, define a chain complex where C is given by this free group so this is the free abelian group chain complex we're working with everything we're building here. The free abelian group generated by critical points of F. And now we can define a differential on this. So a differential is a map D from C to C. And now because C is a free group, so to define a homomorphism of free groups, we just need to specify a matrix. And we specify the image on each generator as a linear combination of the other generators. So for every generator, let's call that, so we already have notation here, so Pi, and that's mapped to a summation of so Pj, and let's call this coefficient Aij, Pj. Let me actually add a bracket here to indicate that so this is the corresponding element that generates the free abelian group, where Aij is defined as follows. So, Aij is 0 if the index of Pj is not equal to the index of Pi minus 1 and equals the number of gradient flow lines from Pi to Pj if these numbers are exactly the same. So here by gradient trajectories, let me just give an example. So if this is M, and let's say f is the height function, it just projects this close to M. So then it has 4 critical points. These 2 are saddle points, and these, the top one and bottom one, are maximum and minimum. Then the gradient flow lines is defined by just looking at the gradient vector field. And so the gradient vector field would look something like this. Well, this is actually, so that's the convention we should use. This is the negative of gradient of f. That's this. And then we look at the flow lines that start from a critical point and ends at a critical point. So for example, in this case, we see that there are 2 flow lines between those 2 critical points, and they look something like that.
But you don't assume that I is less than j.
We assume we assume the index of j is less than the index of I. Right. So if the value of pi is already greater than if the value of pj is greater than the value of pi, then automatically there's no flow line. So and this is a sign counting in the sense that everything is oriented and we count these plus minus signs. So it turns out that again there's another theorem, and this theorem is probably goes back to Stark and Smell, which states that for a generic f, the number of flow lines above is finite, and the orientations are defined. So this is basically some kind of transversality result, but not for transversality as regular values, but for transversality on some kind of modular space of flow lines.
When I was told there were Morse inequalities, so there was a special case of this, Morse inequalities?
Yes, Morse inequalities, I'll talk about that. Morse inequality is a special case of this. So first of all, we know that for generic f, like everything's well defined, and then the homology of C and D is isomorphic to the homology of f. And in fact, this whole thing is graded. So if we just look at this definition, the value of npj actually defines the grading on C. So this whole thing is graded, and the isomorphism actually preserves the grading. And in particular, this implies the Morse inequality, because then that means the rank of the homology of M is a lower bound of the rank, equals the rank of the homology of C, which of course is a lower bound of the rank of C itself, which equals the number of critical points we have on the manifold. So the corollary, so the number of critical points equals the rank of C, but that's greater than or equal to the rank of a homology on C, and this equals the rank of H star. And in fact, this theorem works for any coefficients. So whatever coefficient we choose, we have a rank like this. So that's the story of Morse theory, and in fact, this is so this way of viewing Morse theory as a chain complex. This way of looking at this Morse homology as a homology defined by a chain complex whose differentials come from common flow lines has a generalization to the infinite dimensional setting. So now I'm going to talk about the infinite dimensional picture. I'm going to start by talking about closed ring manifolds, but then like manifolds with link singularities are kind of a generalization of that. So that was actually Fleur's idea. So let's go to Fleur theory. So there's actually there's a funny story. So before Fleur came up with this idea, everybody believed that this Morse homology has no generalization to the infinite dimensional case. This is because if we go back to the proof of all of these, something that corresponds to index npj actually corresponds to a handle attachment of index npj. And we know that if we attach an infinite index handle, that corresponds to like taking a connected sum with, or point sum with S infinity. But we know that S infinity is contractible. It doesn't carry any topology. So for that reason, people have believed for a long time that this whole story can only work if all these numbers npj and npr are finite.
But Casson did something with infinite.
Well, yes. In fact, and also mirror. So you can do something. So there's this negative index and positive index. So if only one of them is infinite and the other side is finite, then we can still do something like this. But if both sides are infinite, so if you have Hessians that are infinite dimensional, like self-adjoint operators in the sense of functional analysis, and it has both an infinite positive spectrum and infinite negative spectrum, then people believe that there's no hope for these stars to generalize, until Fleur basically just proved otherwise. So Fleur had this idea that we can, so in that case, what Fleur's idea was that we just forget about this Morse isomorphism. We just forget about the right-hand side of the equation. In the infinite dimensional case, the right-hand side actually doesn't actually carry a lot of interesting information. In a lot of cases, can be directly computed. It's usually a boring space. But what Fleur realized that in the infinite dimensional case, we can still just look at the left-hand side, and it turns out that this left-hand side carries very subtle information about the topology of three-dimensional manifolds, or in general, the kind of geometric structures that we're looking at. So I'm going to talk about a version of Floer theory that is mostly closely related to flat SU2 representations. So, of course, when we talk about SU2 representations, another way of looking at that is the representation corresponds to a flat SU2 bundle. So we have to talk about principal bundles here. So suppose we have a three manifold, and we consider an SU2 bundle over M. And in this case, there's a lot of terminology from differential geometry, but the punchline is that there's a space, which nowadays usually denoted by this calligraphic A, is to be the space of connections on P. So connections is the structure that we use to define this like generalization of the Levi-Civita connections that allows us to take derivatives. And for this space A, we have a function, there's a Morse function on A, whose critical points, there's a function that's not necessarily Morse, but its critical points are exactly given by flat connections. So, and that's called the Chern-Simons function. So, it's called functional instead of function because now it's defined on the on the space of all connections, which is kind of a function space. So that's denoted by Chern-Simons, and it maps from A to R. Actually, I'm not going to be very careful about that, but technically it's like R to 4 pi R or whatever, or 8 pi R, I can't remember, depending on the, 8 pi. So let's just say the R over Z. So it's probably 8 pi Z or 4 pi Z, depending on the constant convention that we take. So we have some kind of function, and moreover, Chern-Simons, the critical points of Chern-Simons at a connection, let's call it connection A, equals 0 if and only if A is flat. And therefore, or let's call the modular space of A in A such that Chern-Simons, nabla Chern-Simons A equals 0, this actually has some kind of isomorphism with space of SU2 representations of pi 1 of M2 of pi 1. Well, technically, both of them should, to make it correct, like both of them should be quotient with equivalence relations up to a change of coordinates. So on the right-hand side, this is quotient by the conjugation relations, but eventually we have a one-to-one correspondence of that. So the whole idea of instant Floer theory is that we can apply the idea of Morse theory, and we build up some kind of chain complex from the Chern-Simons function. So the general idea, and a lot of PDEs are involved here because, as you can see, we're talking about functional spaces. So this Chern-Simons functional is some kind of energy functional given by the integrals of derivatives of connections, and of course curvature functional. That's a first-order differential operator defining connections. So there are a lot of PDEs going behind the curtain, but eventually the general idea is that we can perturb Chern-Simons functional so that it becomes Morse and satisfies the Sartre-Smale condition. This is a condition that guarantees that the content flow lines is finite, and define a chain complex using its critical points and flow lines.
So remind us once more, what is the space, this infinite dimensional space?
Yes. Let me just
sure, finish.
Points and flow. So the space.
Because you have connections, and then you limit connection to flat connection.
Yes. So the space of connections is a affine space, where so it's not a linear space because it doesn't have a 0 point.
Yeah.
But if A1, A2 are both in A, then A1 minus A2 is a section of, well, actually, since we're talking about three manifolds, so every SU2 bond is trivial. So in that case, it's a section of T star M tensors the algebra of SU2. So it's in a fine space. And of course, to make this really work, we have to work with some kind of balanced manifold. So these are with subleaf regularity and this stuff. And it's a direct computation that's the A dot equals nabla transinus A. Let's see. So this is so if you look at this kind of equation, this equation is an equation M cross R, because now we have a time direction. So if you look at the flow line equation, negative sign here. We have a flow line equation, then we have a time direction, and then this becomes equation M cross R, depending on the orientation. Yeah, I think people usually write R cross M because there's three orientations reversed. So in this equation, so we have an equation on some kind of pullback SU2 bundle on this product manifold, and this flow line equation is exactly the Yang-Mills equation on dimension 4. So this is ASD Yang-Mills equation. It's given by inherited consequences. So a lot of this research were actually first motivated by physics, because this equation actually describes the weak electromagnetic interactions in quantum field theory. But it just turns out that later in the 80s and 90s, people realized that, and it was all followed from original ideas Flirt, is that if we think of this, if we interpret this as the flow line equation, and we interpret flat connections as the critical points, then we can define a chain complex by counting solutions to PDEs. And it turns out that everything works out. We have d squared equals 0, and we don't exactly have an identification like in the previous case. We don't exactly know what this homology theory is, and that's why it's so powerful, because this homology is not equal to anything we have seen before. So unlike the Flirt theory case, where we show that the homology is just isomorphic to the singular homology or singular homology, this homology is not isomorphic to anything we know from other constructions, but it can be used to study the topology of three manifolds. First of all, this homology, once it's constructed, it already gives us a three-manifold invariant, because it turns out this is always a finite-dimensional homology because of some kind of compactness result from analysis. And this already gives us a finite-generated homology invariant for three manifolds. It actually, there's a lot of technicalities here, so for this version, it only works on integer homology spheres.
It's now mathematical theory, it is not physical level.
So
it is precise theory. It is proven, it's not only conjecture.
Right, it's mathematically rigorous. It's completely proved.
I remember this 35 years ago when people were taking just all connections and they said take integral of all the connections, and then always adding, but measure is not defined.
Thank you very much. Yes, so in physics, what people usually do is that people define some kind of function on A and then just integrate that function on A, and that's not mathematically well defined. But this line of ideas, like looking at is critical points as a Morse function, and looking at flow lines and use the Morse homology argument to build a homology theory, that's completely mathematically rigorous. All the moduli spaces that are involved, all the solution spaces involved are elliptic systems. They have nice Fredholm theory. We have proved compactness to show that the countings are finite, and we have everything. So this package is complete. At least for integer homology spheres, we have a complete package. So this allows us to actually apply Flirt theory and this kind of idea, this line of ideas, to study the properties of three manifolds. And in particular, in this case, as we see, this moduli space is very closely related to flat SU2 connections, which is related to representations of the fundamental group. So let me just write some general ideas. So outline of proof of our main theorem. So there's a variation of this idea that applies to links. So in general, if we have a link L in S3, then there is a Flirt theory associated to this pair. Roughly speaking, it's kind of the Flirt theory that views this manifold as an orbifold, where L is the singularity, And so we changed this equation. So all these equations are changed, but they changed in a controlled way. So in the sense that if S3 admits a double branch cover over L, it's pretty much just an equivariant version of Floer theory on the double branch cover.
But this involution is important then.
Oh yes, so having involution instead of some like other number is important for technical reasons. It's actually important so to make sure that this thing is actually a finite count. So it's like it's called monotonicity in Floer theory. It's just because like there's a very technical step that to show that this is finite, we have to know that like everything has a bounded energy, and that's like has to do. It only exactly works if this is a double branch cover. It just happens to be the case. So there's a Floer homology associated to this pair, where in this case, critical points or the set of critical points corresponds to the set of meridian traceless representations of pi 1 and 3 minus L in SE2. And now, what we show is that if that link L only contains abelian meridian traceless representations, then up to conjugation, there are exactly 2 to the n minus 1 of those, when n is the number of common components. So that follows from the previous argument that we used. So abelian traceless representations is exactly 2 to the kinetic components of L minus 1. And the first theorem we proved, or let's call it a proposition, is that if so it only has abelian traceless representations, then the instant homology, so this is the notation we write it, is actually just freely generated by these critical points. And then, let me just write very, so if this condition on instant homology holds, then we can use tools from Floer theory to study the property of L, and then we can show that if this holds, then pi 1 and 3 complement L admits irreducible either admits irreducible representation, irreducible traceless representation, or L is the connected sum of this. So this part of the proof involves some fairly technical detection argument from Floer homology theory. So I'm not going to talk about that. But let me just remark on this property. So the proof of this property is actually kind of funny because, so let's recall it. So if we know that these are only abelian traceless representations, then we know that this homology has this many generators. But then, in general, we don't quite really know if this is already a Morris case. So if we have to take a perturbation, then we completely lose track of the number of generators or the critical points. But it turns out that by a computation, the Chern-Simons functional is non-degenerate at abelian representations, if and only if the H1 of the double branch cover has no torsion. In other words, if and only if its determinant is 0. So if its double branch cover has no torsion, then this pretty much follows, because now we have all the critical points, and we can show that there's no flow lines between them, and this follows. If it does have a torsion, then that means that it has a non-trivial Fox coloring on the arcs. And we can turn that Fox coloring into an irreducible representation as it is. So that is the part that we used something that's related to double branch colors.
It has homology of cover. Yes.
Yeah, real homology. So yes, and then the second part is like heavy Floer homology argument, and we use the excision formula that we proved before to study this question. All right, so I think that's the end of my talk. Thank you very much for your attention.
And let me